Hello everyone, welcome to this webinar on Introduction to GPSX, New Greenhouse Gas and Carbon Footprint Module. My name is Rajiv Goel and I'll be showing you through this module, the new module of carbon footprint which we have put together in GPSX. And I have my colleague Spencer Snolling here who is coordinating this webinar.
Hello everyone.
So today's agenda is going to be, I'm going to provide you a little bit of an introduction about the carbon footprint module which we have implemented recently in the latest version of 6.2, GPSX 6.2. I'll talk about a little bit about the model structure, just to give you a feeling about what kind of equations we have used, and provide you a demonstration of the model as well so that you feel comfortable when you start using the model in GPSX. Finally, we'll start with, we will entertain a few questions if you have, and we'll try to provide those answers. If we can't get back to you on your questions, we will try to contact you individually and provide you the answers. So first of all, in a wastewater treatment plant, there are different sources of greenhouse gas emissions. By greenhouse gas emissions, we mean basically the production of CO2, methane gas, and N2O from the processes. So if we look at a wastewater treatment plant, we can see that emissions can take place from aeration tank as a CO2 or N2O. From anaerobic digester, we can expect CO2 production and methane production. Also for anaerobic digester, we use sometimes heating fuels which generate carbon dioxide. In addition to these process emissions, we also have a lot of pumps in our wastewater treatment plants and blowers for aeration tank. So all these consume electricity. This electricity coming from outside sources also require, also produce some carbon dioxide into the atmosphere. Also, in a wastewater treatment plant, we consume some chemicals and also some materials. So all this electricity, chemicals, and materials, they give rise to greenhouse gas emissions from the wastewater treatment plant. So in a carbon footprint estimation exercise, we want to quantify different emissions which are taking place in a wastewater treatment plant and try to see what are these emissions related to, whether they're related to process emissions, whether they are coming from the electricity consumption or they're coming from the fuel consumption part. So when we try to do carbon footprint estimation exercise, we have to give attention to process configuration because the greenhouse gas emission can depend on the process configuration. For example, if you have nitrification, denitrification type of configuration, you might expect some N2O production. Also, if you have anaerobic digester in your configuration, you can expect carbon dioxide and CH4 production from anaerobic digester. Also, depending on the source of electricity, the emission factors associated with the electricity basically are region dependent, and they can actually affect the carbon emissions estimated for a wastewater treatment plant. Also, we look at operational factors, for example, SRT and DO concentration in aeration tanks can affect the production of CO2 and N2O coming out from aeration tanks. Also, the influent composition, for example, COD to nitrogen ratio can make quite a substantial effect on the N2O production rates from aeration tanks. Also, sometimes we want to evaluate the effect of dynamic conditions on the carbon emissions or the greenhouse gas emissions. And if we try to look into all these factors and try to incorporate all these factors into our estimation exercise, we can see that this becomes a very complex exercise, and it might take a few days to weeks of effort, and it is not a very trivial exercise as such. So considering all these aspects, we try to come up with a solution. We have a model called Mantis 2 model, which is a comprehensive process model. So we do already have process modeling capabilities in GPSX, and very good models to actually model the process component of a wastewater treatment plant. So what we try to do in the new development is just to include carbon footprint models, which means that we try to include the gas emission rates, estimation of gas emission rates from different reactors. Also try to estimate the electricity consumption in different unit processes and the heat requirements. So those kind of extra calculations we try to add in the process model of Mantis 2. And we are calling this new model as Mantis 3. And this model can actually do both the process and the carbon footprint calculation for you. And just to highlight some of the advantages of Mantis 3, well, the biggest advantage which we see having one platform for doing process performance and carbon footprint evaluation. So basically, what you can do is you can have just a single platform or a single model, basically, which can do process calculations for you and also help you to evaluate the greenhouse gas emissions from the plant. When we use this kind of models, basically, we don't really have to duplicate the input. For example, if you're using one platform for doing the process calculation and then you're using another platform for doing the carbon footprint calculations, then you need not provide all the information which you have provided in the process model again in the carbon footprint model. So basically, you avoid duplicating information, providing duplicate information into two different platforms. Also, one of the benefits of using the models which we implemented GPSX, that these are dynamic models, so you can also do dynamic analysis of the greenhouse gas, the quantities of greenhouse gas which are coming out from wastewater treatment plants. Also, it helps you to evaluate different operational and configurational changes in your layouts. And by using this platform, actually, you can reduce the days or weeks of work to minutes to hours, basically. So now I'll kind of, with this introduction, I'll go into describing a little bit about the details of the models. So first of all, we have categorized emissions from the wastewater treatment plant into 3 different categories based on the scheme proposed by International Panel for Climate Change, IPCC. So what we are trying to do here is we have 3 categories which we are calling Scope 1, Scope 2, and Scope 3 emissions. In Scope 1, we are kind of quantifying all the emissions which are taking place at the wastewater treatment plant. For example, the emissions which are counted in this scope are the emissions like CO2 from anaerobic, anoxic, and aerobic biological processes. Also, N2O production from nitrification, denitrification, and CH4 production from anaerobic processes. Also, any additional fuel which is consumed for heating purposes at the wastewater treatment plant, any emissions associated with that fuel consumption are also accounted in direct emissions. In the Scope 2 emissions, we are actually quantifying all the electricity consumption arising by using the pumps or the blowers or any other electrical devices at the wastewater treatment plant. So all these electricity consumptions are estimated and then converted to carbon emissions depending on region-specific emission factors for electricity source. In Scope 3, we are estimating all the chemical use and the material use which happens at a wastewater treatment plant, and also we are also incorporating the transportation emissions or the emissions which arises due to the transportation of these chemicals to and from the wastewater treatment plant. So this is a kind of overall scheme, and when we are reporting all these emissions in GPSX, we are reporting them as Scope 1, Scope 2, and Scope 3. In addition to emissions, we have also included offsets, and these offsets basically are this is kind of an accounting kind of a system in which we are, for example, trying to estimate all the emissions for CO2, but some of the emissions of CO2 might be coming from, for example, biogenic sources. So these biogenic sources, the CO2 which is being emitted is kind of carbon neutral. So in a way, you estimate the emissions and then also estimate the offset which are arising due to the biogenic fraction of carbon which is coming into wastewater treatment plant. And you can use the emissions and offsets actually to estimate the net greenhouse gas production from the wastewater treatment plant. So in the offsets, again, we have categorized them into scope 1, scope 2, and scope 3. In the scope 1 offsets, we have the offsets for U for a biogenic fraction of carbon, which means that, for example, if we are looking at a domestic wastewater treatment plant, then most of the carbon is from biogenic sources, and any carbon dioxide which is emitted will be actually also will provide an equal offset to the emissions. Also, if CH4, for example, is being produced from anaerobic digester, you can use it, and if it is not being released to the environment, you are flaring it, or you are using it to basically recover heat or electricity, then you can actually generate some offsets to the emissions. In scope 2, at present we don't really have any offsets implemented in scope 2, and also for scope 3 we don't have any extra offsets implemented right now. Just to give you an idea about how we are estimating scope 1 emissions which are arising due to the process emissions, what we are trying to do here is all the emissions which are coming from the processes are being estimated as a gas-liquid transfer process. For example, when an organic substrate is being converted, metabolized basically, and part of this is converted to biomass, and part of this is kind of oxidized, leading to production of CO2. And the CO2 actually, depending on the pH of the system, can remain in the solution or can remain as CO2, which is actually at a gas-liquid boundary is actually transferred to the atmosphere. Also, similarly for anaerobic process, we are producing methane gas, and through a gas-liquid transfer process, it also gets into the atmosphere. For nitrous oxide, we have the process of nitrification, and then actually going to denitrification, which produce N2O, and leading to nitrogen. And this intermediate of N2O is also basically can get stripped through the gas-liquid boundary and gets into the atmosphere. So all these gas-liquid transfer equations for each of the greenhouse gas are implemented for each unit process or each reactor in GPSX, and all the estimations are based on using the gas-liquid transfer process for each gas. So if we look at the equation for estimation of the emission of the gas, it's a KLA-based equation in which we have the gas mass transfer coefficient and the driving force, which is dependent on the equilibrium concentration and the actual concentration in the liquid, and the volume of the reactor. And this is a kind of a global warming potential of that particular gas. For example, if we are estimating the N2O emission, then this factor is going to be like 298 or 310. So that way, all the gas emissions are being actually estimated as gram CO2 equivalent per day in the model. Also, for the energy emissions, we are trying to estimate the total pumping energy, total blower energy, and total miscellaneous power which is required for each individual unit process, and trying to estimate the total electricity consumption for that unit process. Then we try to actually multiply that total energy consumption with the region-specific emission factors, which are then multiplied by the global warming potential factor. For example, if for 1 unit of electricity, consumption, there is some methane production associated with this 1 unit electricity production, then that methane is converted into CO2 by multiplication of these factors. So all these scope 2 emissions are also reported as gram CO2 equivalent per day in the model. Also, for the materials, we are estimating the total material consumption in the plant and then also multiplying it with a kind of emission factor which is directly in terms of CO2 equivalent units. And one thing I would like to mention here is that when we are doing the carbon footprint for the wastewater treatment plant, we are not estimating the materials which are consumed or the CO2 associated with the material which is used during construction. So that is not included in the model. So what we are trying to look at is the operational part of the CO2 that is being emitted from the wastewater treatment plants. To complete the model, basically we have some built-in database into our GPSX system, and these databases basically include the regional electricity emission factors for different regions in United States, and all this data is coming from Environment Protection Agency's E-grade data from 2010 report. Also, we have some data for Canadian regions, and this data is coming from Environment Canada's 2008 report. So all these factors are built into the model. So once you select where the wastewater treatment plant is located, then you can those factors are automatically used in the model in the estimation procedures. Also, for estimating the carbon emissions associated with fuel consumption in the wastewater treatment plant, we do have some database for fossil fuel emission factors, and this database is coming from the Climate Registry website. So once, for example, if you're using different kind of different fuels, for example, in anaerobic digester, if you're choosing a fuel, then those factors, the CO2 associated CO2 emission factors, are automatically picked up from this database. Also, to further complete the model, basically we had to implement N2O production model into Mantis 2 model. And the model which we implemented for N2O production by heterotrophic bacteria is coming from Hyatt and Grady model published in 2008. And for the N2O production by autotrophic bacteria, we are using the references from NE and Mamfe. I have to say that these are experimental models at this stage, because there is still the consensus is not fully developed with respect to autotrophic, with respect to N2O production by autotrophic bacteria. So we intend to modify these models as further research comes to light, and keep on improving the structure of this model here. And I would like to give you a small demonstration of the model by using GPSX. So most of you are familiar with the GPSX platform, and this is a very generic wastewater treatment plant which I have here on this drawing board right now. It has an influent object. It has aluminum feed for phosphorus removal, a primary clarifier, aeration tank, secondary clarifier, and effluent. In the solid train, we have the sludge from the primary thickener goes into the primary clarifier, goes into the thickener, combined with the waste activated sludge, which is going to the thickener, and the thickened sludge is fed to the anaerobic digester, and we are withdrawing the digested sludge and taking it for further disposal. So this is a very general kind of a process, which typical wastewater treatment plant process, which we would like to, which we see very common layout. And here, once all the process inputs are set into this system, for example, the sizing of the primary clarifier, the sizing of the aeration tank, and sizing of secondary clarifier. Once all those information is fed into the model, if we want to add extra information for doing the carbon footprint modeling, then we need to provide information about, for example, how much is the pumping power, how much is the blower power, and those are the steps which I would like to show you now. So the first step, actually, I'd like to say, is to make a global setting for running your model. So if we go to the drawing board and right-click on the empty space there, if we go to System, Input Parameters, you can see there is a new item there, which is the carbon footprint. When you click on this one, you can see there is some information with respect to CO2 equivalents that are used for converting, for example, methane emission rate to CO2 equivalents and N2O to CO2 equivalents. In literature, you will find, depending on the time frames, basically you can find different factors. Sometimes you will find factors of 22 and 310 for nitrous oxide. So you can change these factors if you like to change. If you want to use different factors, you can change it here. Also, another thing is you can specify in which region your plant is belonging, where this plant exists. For example, right now we are using Canada, Ontario, but you have quite a big list of the regions where to choose from, basically. And once you have chosen this, then region emission factors, you can see the database here. So right now we are Canada, Ontario, and you have the CO2 intensity per kilowatt hour here. So all those factors are built into this database. Also, you can specify how much percentage of the fraction of incoming wastewater is coming from the non-fossil carbon. So for example, if there is an industrial source and it's coming from, it has some fossil fuel carbon built into the influent, then you probably would like to change this fraction to a lower number. Also, for the fuel calorific values, we have this database and the number of fuels to choose from. By default, the fuel selection is natural gas, and we have the calorific value for this fuel here, and also the emission factors here. So in essence, what you need to do is you need to probably choose your region where the plant exists, also specify what percentage of the non-fossil carbon is there coming into the wastewater treatment plant. Also, if you want to change these factors, you can change that here. So once you have done that, then the second step is basically to specify how much of the power consumption or the, for example, the pump power for each individual unit process. For example, if we are in the influent, then you can go to composition and operating cost, and you can specify the hydraulic head, pump efficiency, and the pumping head loss. So once you provide this information, since we have already provided the flow information, it automatically uses this information and the flow information to estimate what is the pumping energy requirement for this individual unit process. So if you go to each unit process, you can find menus to specify energy consumption or to quantify the energy consumptions required for the pumps. For aeration tank, we have operating costs in which you can actually estimate, or you can provide the blower, basically the parameters for the blower, and depending on how much air supply is needed for this unit process, we can estimate, the model estimates how much energy consumption will be required due to aeration. And similarly, for other unit processes, you can specify the pumping power or the pumping head loss and the energy and the motor efficiency, those kind of factors for making the model capable of estimating what energy consumptions are required for each individual unit process. For anaerobic digester, we have two additional menus here. One is a digester heating requirement, in which actually in most of the situation we need to heat the digesters because we want to maintain the temperature at 35 degrees C. In those specific applications, there is some external fuel which may be used at a wastewater treatment plant. So you can select different type of fuels which are provided here for heating the digester. And there are some inputs which are required here just to specify what is the ambient temperature of the air, what is the temperature of the incoming sludge, specific heat of the sludge, and heat exchanger efficiency. Also, we are estimating what are the heat losses to the different, from the walls of the digester, from the roof of the digester, and from the bottom of the digester. So you have different selections there, and which you can use to specify the problem. And based on that, it's going to estimate how much heating or how much heating requirement or heating energy do you need for heating the anaerobic digester. Also, we have energy recovery options for the digester, in which we actually provide you the option to use the gas for the boiler, or you can use it for combined heat and power unit, where you can recover heat or electricity. And if you are not using any of these heat recovery options, then you can probably flare the gas, and you can also specify what is the flare efficiency in this menu. Based on this information, the model estimates what kind of offsets you can, emission offsets you can gain, and those offsets are reported as the output of this model. So after you have done all that information, providing the pumping power, the blower power, the heat requirements, the fourth component of specification is the chemical requirements, basically. So if you go to the chemical dosing object, you can see there is a new menu item, carbon footprint. If you click on this, you can see greenhouse gas emission factor associated with aluminum ion consumption. So we have some values here, and also for shipping this material to and from the wastewater treatment plant, you can specify the truck capacities, the fuel efficiencies of the truck, and the distance of the tanker trip. So in this particular way, we can estimate what are the emissions associated with the transportation of these chemicals in the model. So once you specify all that information, we can actually go to the simulation mode and try to show you how the outputs of these models looks like. So I'm just going to run this model for a default scenario, and we are going to look at all the outputs there. So this solves the model, and this is a new functionality in GPSX 6.2 that you can export or display all the information for every stream. For example, all the streams are there, and you can display all the concentrations and the mass flow rates for each stream for different kind of components in the wastewater. So you can see all the information. This is a process information. For a greenhouse gas information, if we go to greenhouse gas tab here, we are displaying all the information related to, for example, scope 1 CO2, scope 1 CH4, scope 1 N2O, scope 1 emission total. So we are basically describing the emissions of each gas in each scope, and then we are trying to specify all the offsets which you gain from each object, which you can get from in each object. And finally, we are estimating the net footprint for each object. So for example, if we look at the influent model, we can see that the scope 1 emissions are not there, because we are not emitting anything from the influent object. The only emissions coming out are from the energy consumption. So that's the pumping energy, which is required to pump the influent from the influent to the wastewater treatment plant. And those are the emissions we are estimating here. Total carbon emission 98 tons CO2 equivalent per year. And similarly, you can see for different unit processes what are the categories of each emission. So here, if we look at, for example, the aeration tank, we can see that there are some process emissions which are happening, so scope 1 emissions. And in the scope 2 emissions, we have some of the offsets basically here, because most of the carbon is the biogenic carbon. So we are taking some of the offsets there. So if we look at the net emissions coming out from aeration tank, these are 3,660 tons of CO2 per year. And most of this emission is arising from the production of N2O from the aeration tank. So this gives you a very quick overview of all the emissions taking place at different points in the plant. And if you want to look at the total emission, we also actually can sum up all the emissions happening at the total plant, and then the total emissions which you're estimating are 6,815 tons CO2 equivalent per year. So we're running out of time a little bit here, but one thing I want to say is that you can actually conduct, you can actually see the effect of different variables. For example, if there is influent flow, and if you want to change the flow, you can see how the emissions of N2O and CO2 basically are going to change in aeration tank and what impact it will make on anaerobic digester emissions. Also, for example, the DO set point will just, if you change this variable here, also again you can see what effect it's going to make on the total emissions. So just for the sake of it, we can just run it at 1.8. So right now, our emissions are 6,815 total emissions. If we run at a DO point, set point of 1.8, we can see that our emissions go up to 7,400. And part of this increase in the emission, if you analyze the data further, you will see that it's coming from extra emissions which are taking place due to extra N2O emission coming out from aeration tank due to more denitrification going on in the system. So you can conduct all this kind of analysis and try to see what effect different operational strategies make on the emissions, and evaluate your process configuration and try to optimize it with respect to minimizing the greenhouse gas emissions from your plant. So you can further go into actually individual unit process, and we have more information with respect to carbon footprint. For example, if you open this up, you can see further classification of different items. If you want to look at individual items, you can see the more details for each unit process. So there are many more actually outputs which are built into the aeration tank. This is just a kind of a summary table which I try to show you here. So I guess this gives you a little bit of a kind of a flavor of the new model. And one thing which I forgot to mention, well, you should notice that here we are working in Mantis 3 library. So all these options are available only in Mantis 3 library. Here in this top bar, you can see that the selection of the library is Mantis 3 library. Now I'll go back to our PowerPoint there and just try to wind it up. And just to conclude, well, you can see that the new module actually significantly simplifies the task of carbon footprint estimation from wastewater treatment plant. It's a kind of a, we are trying to say this is a holistic tool because it does the process as well as the carbon footprint calculations for you. And it provides you with the options of easy input, easy output. Also, you can do both steady state and the dynamic analysis for the wastewater treatment plant. And lets you do the process evaluation and also the process and the operational alternatives. Like you can change those. You can make changes to your process, all your operational variables, and try to see what impact it makes on your carbon footprint, basically. So with this, I would give it to Spencer.
Thank you, Rajiv. What we're going to do now is entertain some questions from the group here. I've seen as we've been as Rajiv was speaking, we had several questions come up already. So If you have any further questions that you'd like to ask Rajiv, please type them in the question box now. Normally at this point I would say a few words here about our other products and services that we offer. I think since we're running a little bit long, I won't dwell on them in a great detail. I'll mention again our SimuWorks interfaces. These are some of the examples of the custom look and feel that we can provide for any GPSX model, and this would include a carbon footprint and greenhouse gas emissions model. That information could be incorporated into one of these types of SimuWorks custom interfaces. We also continue to offer a number of services related around the use of our software. We provide standard and advanced training. We can do that actually via webinar, just like we're doing today. We can also be hired to carry out modeling consulting projects on your behalf or in coordination with you. We can help you provide information for your calibration of your models, design sampling programs, bench scale studies to get the data that's required to calibrate your model. Assist you with research and development of brand new models, and also customize the existing models that are part of GPSX so that we can meet the needs of how your plant operates in reality. I will mention, before we move on to our questions, that the next upcoming webinar is going to be discussing the GPSX toolbox object. So you may or may not have investigated the contents of the GPSX toolbox in the past. There's a number of tools there to be able to make your model do things the way that it might happen in reality, to schedule things to be turned on and off, and other types of control systems and samplers. And so there are a number of useful little tools there which we'll go through in detail. March 19th at 2 p.m. Eastern Daylight Time, you can click on the webinars tab at our website to register, and we hope to see you then.